Hello students, this is Dr. Siva Nagaraju from IARE. Today we are going to discuss elements of digital communication systems and pulse code modulation. So before going to the topic, first what is a communication? What is a communication? So communication means we're transferring information from one point to another point. So the first point we can call as source or transmitter, and the second point we can be called as receiver or destination. So in this topic, what are the elements involved for transferring the digital information from source to destination? So this we can call as elements of digital communication systems. And second one is pulse code modulation. So this is the first digital communication system. So in this session, we are going to discuss what are the elements involved in the digital communication system and the pulse code modulation. Okay, let's start the session. So this is the block diagram what we used for the digital communication system. So we must require a source. So that is the digital source. And the second block is a source encoder. Source encoder. And second one is channel encoder, and third one is modulator. These three can be called as transmitter. So in the transmitter, first we require an information, that is the digital information. So the digital information is going to encode in the source encoder. So what is the duty of this source encoder? Here, the main function of the source encoder is to represent the information in a compact form. Compact form. So the output of source encoder we can call as source code word. So the source code word is the less codes. It means it contains less codes. Why? Here the source encoder removes the redundancy. Redundancy means not essential bits. So those bits are removed by the source encoder, and the produced code you can call as source code word. Okay? And next, the source code word is applied to the channel encoder. So the channel encoder duty is adding some parity bits to the original source code word. And the output of this channel encoder we can call as channel code word. Now, the channel code word contains more number of bits than the source code word. Why? Because here the source encoder removes the redundancy, but the channel encoder adds the redundancy. Why? By using this redundancy in the channel encoder, we may detect the errors and we may correct the errors. So, in the digital communication system, here the algorithms which used for source encoder is Huffman and Shannon-Fano algorithm. By using Huffman and another one is Shannon-Fano. So these two algorithms used for removing the redundancy in the information bits. So it produces source code word. And the channel encoder, here we may use black codes, cyclic codes, convolution codes. So this is used for the channel encoder. And third one, important one, what is used in the transmitter is modulator. So here we used different type of modulation techniques. Why? Because here after modulator, my signal which is going to enter into the channel, here the channel is which accepts analog or waveform, but whatever our information is in the form of bits, digital bits, means ones, zeros, like that. So we are going to convert this baseband signal into passband by using these modulators. So here we know the modulator which performs the modulation process. So already we know that what is a modulation. Here we are going to varying some of the characteristics of the carrier signal in accordance with the instantaneous value of the message signal. So that is the basic definition of the modulation. So by using carrier, here we are going to change over bits into waveform. So here my input to the modulator is ones and zeros. So that is it may be bits like that. So these bits I am going to convert into waveform. So here I may use ASK, PSK, FSK, QPSK, DPSK, or any array techniques. Array techniques. So out of these, I may use any one for converting these digital bits into waveform. So after conversion these bits into waveform, now it is ready to launch into the channel. So after launching into channel, noise will add up. So that's why we can call it as additive white Gaussian noise. So this noise will going to add with our signal, and the signal is going to corrected. So in the below box we are having receiver. So the receiver which is going to receive that noisy signal. Why? Because noise plus our signal. So simply noisy signal is received. So here our aim is we are going to estimate what that user that source is sent and the exact information which is given to the user or from source to destination. So the receiver again contains three important blocks. That is one is a demodulator. That is exact reverse operation is done in the receiver. Whatever done in the transmitter, exactly reverse. So wherever the last block of that transmitter is modulator. So in the receiver, the first block is a demodulator. So the demodulator which is going to estimate the channel code word from the received signal, and this is given as the input to the channel decoder. Why? Because I am using a channel encoder at the transmitter. So the reverse operation is done in the decoder. So as usually source decoder also having. So the final output of the receiver is estimate of message signal. So here we are going to estimate whatever the source is sent. So why? Because here I used the digital bits like ones, zeros. So at the end of the receiver, I also received those ones and zeros. Okay. So this is the block diagram of digital communication systems. Okay. Coming to the next slide. So here the first one is source encoder. So the source encoder and channel encoder, modulator, whatever is coming in the transmitter of this our digital communication system block. So here the function what I given, the source encoder comprises the data into minimum number of bits. This process helps in effective utilization of the bandwidth, and it removes the redundant bits. Redundant bits means unnecessary excess bits. The source encoder function is to provide a compact representation of the message signals. The resulting sequence of symbols is called the source code word. Called as the source code word. So this is the output what you get from the source encoder. Why? Because here we are taking the digital source. This is source. After the source, we're having source encoder. So this is my source encoder. So the information whatever is coming from the source. So the source may contain the unnecessary bits. So these unnecessary bits is going to remove by this source encoder. So that's why here it removes the redundant bits. So after removing the redundant bits, we're having the effective utilization of the bandwidth. Why? Efficient code is produced. By using this efficient code, we can utilize the bandwidth. Why? In communication, the bandwidth is very, very important parameter. So we are going to effectively utilize this bandwidth. For this, here already discussed, we use two types of algorithms for removing the redundant information. So one is we discussed as Huffman coding, and second one is Shannon-Fano algorithm. Shannon-Fano algorithm. So by using these two algorithms, we are going to remove the redundant bits. Now, the output of the source encoder is efficient code. That code is called as source code word. Coming to the next slide is channel encoder. So already we've seen that block diagram. After the source encoder, we're having a channel encoder. So the channel encoder does the coding for error correction. Why? Because after all the process, we are entering the signal we are launching the signal into the channel. So in the channel, always noise will add up. So whenever the noise adds, the signal is going to distort it, and the distorted signal produces some errors. So these errors is going to correct it and going to detect it. So by using this channel encoder, we may go to detect and correct that errors. Okay. So the channel encoder adds some redundant bits to the transmitted data. These are the error correcting bits. So wherever in the source encoder, we are going to remove the redundant. But here, we are going to add some redundant information. So now the channel code word is longer than the source code word by virtue of the redundancy built into its construction. So why? The first one is removing redundancy, and second encoder is adding. So that's why channel code word is longer than the source code word. Coming to the digital modulator. So this is the third block in the transmitter. So the signal to be transmitted is modulated here by a carrier. The signal is also converted into analog form from the digital sequence in order to make it travel through the channel or medium. So the sequence of analog symbols produced by the modulator is called waveform. So suitable for transmission over the channel. So already discussed the channel is in analog form. So it allows the analog signals only. So we are going to convert the digital signals. Why? Because before this digital modulator, we are having a source encoder or channel encoder. So all the bits in digital form. So I'm going to convert these digital bits into waveform. So here I used a carrier. By using that carrier, we are going to convert this baseband into passband. And we have a doubt. Why we are converting this passband? Without passband, we may transmit the baseband signal into the channel. Yeah, you can send. But the baseband signal transmission is not suitable for radio link. Here our aim is to send the information for long distance communication. So our signal which is suitable to the radio link. But whenever it is in baseband, it's not suitable for radio link. So that's why here we are going to convert the baseband signal into passband by using modulation process. So here we use different types of digital modulation techniques. It may be ASK, it may be PSK, it may be FSK, it may be QPSK, it may be DPSK, or it may be MRA. Why? Here we're having two types of digital techniques. One is a binary form and another one is a MRA form. So here I may use either binary or MRA technique depending on the application. Okay. And another one is channel. Here the channel or a medium allows the analog signal to transmit from the transmitter end to the receiver end. Here the channel may be wired or wireless channels. We may use wired or wireless channels. Okay. And another one is a digital demodulator. So this is the receiver first block. So this is the first step at the receiver end. The receiver signal is demodulated as well as converted again from analog to digital. Why? Because in transmitter, I'm converting digital to analog form. So in analog form, signal is going to transmit throughout the channel. And finally, it reaches the receiver. So at reaching the receiver, the signal form is analog, but the user requirement is digital. So here we are going to convert analog into digital form by using digital demodulator. So here the signal is reconstructed. Okay. And another is a channel decoder. So the channel decoder of detecting the sequence does some error corrections. The distortions which might occur during the transmission are corrected by adding some random bits. This addition of bits helps in the complete recovery of the original signal. So whatever the parity bits is going to remove here. Okay. Why? Because at the transmitter, the channel encoder adds these random bits and errors are entered into these random bits. The random bits we may call as parity bits. So with the help of parity bits, we are going to detect the error and we are going to correct that error. And another one, the last one is source decoder. So this is the last block of that receiver. So here the resultant signal is once again digitized by sampling and quantizing so that the pure digital output is obtained without the loss of information. So the source decoder recreates the source output. So now the output of the source decoder is in whatever the transmitter sends information or the original source send information is same as that user required. Okay, so this is elements of digital communication systems. So now what are the advantages of these digital communication systems? So the effect of distortion, noise and interference is much less in digital signals as they are less affected. Why? Because here the analog form signal is easily affected by the noise, whereas the digital signals is not affected. Okay, and another one, digital circuits are more reliable when compared with analog circuits. And third advantage is the occurrence of crosstalk is very rare in digital communication. So whereas in the analog communication, crosstalk is more. Why? Because before digital communication, we are all using analog communication. So in analog communication, the crosstalk interference very severely. When you take a phone call, another phone voice is going to heard by the users. So this is a crosstalk. Okay, and what are the disadvantages of digital communication system also? We are going to discuss it. Why? Because any system having advantages and disadvantages. So here also some disadvantages are there in the digital communication. So first one is there is a requirement for synchronization in the case of synchronous modulation. Why? Because here the detection of the signal may be coherent or non-coherent. If you are using coherent detection, here the synchronization is must and should. When you use the non-coherent, the synchronization is not necessary. Okay. And second one is the most common limitation of digital communication is that it requires more transmission bandwidth. So this is the main limitation or drawback of this digital communication. Why? Because it requires more transmission bandwidth than the analog communication. And also here may be sampling error. So in digital communication, we must use these processes. One is sampling and another is quantizing. So in the next coming slides, we are going to know how to convert an analog signal into digital form. Okay. And now the second topic of this session is pulse code modulation. So the pulse code modulation is the first digital communication system. So after this PCM, we're having a DPCM, differential pulse code modulation, DM, delta modulation, ADM, adaptive delta modulation. So like that, the advancement in technology is moving. But the first one is pulse code modulation. So in PCM, how the signal is going to be represented and how the digital is coming from that analog signal. Okay. So in PCM, a message signal is represented by a sequence of coded pulses, which is accomplished by representing the signal in discrete form in both time and amplitude. So here we are going to convert both time and amplitude. Why? Because in any analog signal, we're having three parameters. One is amplitude, phase, and time. So here in analog, it may be pulse amplitude or pulse width modulation or pulse position modulation. Here our time is going to discrete. That means by using sampling, here we are going to samples like this. That means here time is going to discrete, but amplitude in log form. So here I am going to convert this continuous amplitude into discrete form by applying quantization. That means here I am going to like this. I am going to discrete in the amplitude domain also. Already we are having time is going to discrete by using sampling. So here I required two operations. One is sampling and another is quantizing. So by applying these two operations, I am going to convert an analog signal into discrete form. So now the signal is in pure discrete form. So whenever the signal is in pure discrete form, then we are going to encode the discrete signal. Then it is going to convert analog to digital form. Okay. So this is the block diagram of the pulse code modulation. So here I used analog message signal. Why? Here I am going to convert analog into digital form. Okay. So first I required an analog signal. By using the analog signal, I am going to operate different operations like sampling, quantizing, and coding. So these are not seen in analog communication, whereas in digital we are having these blocks out there. So before sampling, we use LPF, low pass filter, and after low pass filtering, we use a sampler. So sampler, we know that which is going to continuous time into discrete time. After sampler, the time will be discrete, but amplitude as usual continuous form. So that's why I use a quantizer. So the quantizer which is going to discrete the continuous amplitude. So now the output of the quantizer is a pure discrete form. So here I got pure discrete. So this pure discrete is applied to the encoder. So the encoder which is going to encode. Here encode means a plan of representing this discrete signal into a bit form. Okay. So now I got to a bits form. And here in the channel, a special arrangement is there in PCM. No other digital system having such type of arrangement. That is nothing but regenerative repeaters. So here, through the channel, we are having regenerative repeaters. These repeaters are generally located 50 kilometers. For every 50 kilometers, one regenerative repeater is going to place. So that is a PCM having the special arrangement. So after channel, we are going to receiver section. So the receiver section having a regeneration circuit, then after decoder, a reconstruction filter, and finally the destination. So this is a PCM block diagram. Okay. Now we are going to discuss the operations one by one of this block diagram. So the basic operations performed in the transmitter of the PCM system are sampling, quantization, and encoding. Already shown in the figure. So before sampling, we're having LPF, that is low pass filter. So here the low pass filter, which is going to prevent the aliasing effect. So here after LPF we are having sampling. So we are going to remove that aliasing. Aliasing means the high frequency signal seems look like a low frequency signal. So I am going to remove all the high frequency signals from the message signal. I am going to remove all the high frequency terms in the message signal. And then after I am going to sampling. So after sampling, I am using quantizing and encoding operations are usually performed in the same circuit, which is called an analog to digital converter. So here all these operations simply you can call as analog to digital converter or simply ADC, analog to digital converter. So these are the operations performed in the transmitter. And what are the operations in the receiver? So the basic operations in the receiver are regeneration of impaired signals, decoding, and reconstruction of the train of the quantized samples. And regeneration also occurs at intermediate points along the transmission path as necessary. So that is called as regenerative repeaters. So along the transmission path means in the channel, we are going to placing these regenerative repeaters for every 50 kilometers. So that's why the signal is going to be distorted very less when compared with other digital systems. Now here sampling. So here the sampling is done according to the sampling theorem. So in order to ensure perfect reconstruction of the message signal at the receiver. Why? Because here my duty or our duty is getting the message signal at the receiver. So that is a perfect reconstruction of the message signal. We must do the sampling. So how the sampling is done? The sampling rate must be greater than twice the highest frequency component W of the message signal in accordance with the sampling theorem. So according to the sampling theorem, we are going to do sampling. So after sampling, my signal will be discrete in time domain. Okay. And after sampling, we're having quantizing. So that quantizing, which is going to convert this continuous amplitude into discrete amplitude. But here I am not discussing about the quantizing. Why? Another session we're having a quantization process. In that quantization process and types of quantizers, we are going to elaborate discussion in that quantizing. Because quantizing is a very important and vast topic. So that is going to discuss separately. But here just I'm discussing about what is quantizing. So quantizing means converting continuous amplitude into discrete amplitude. So after quantization, the signal is in discrete form in both time and amplitude. So whenever the signal is discrete in both time and amplitude form, then we are going to encode. So now what is encoding? An encoding process to translate the discrete set of sample values to a more appropriate form of signal. So any plan for representing this discrete set of values as a particular arrangement of discrete events is called a code. So that means after encoding, the signal will be called as a code. So one of the discrete events in a code is called code element or symbol. That means here it may be represented as like this. So this is code. So in this code, one discrete event is called as code elements. So this is encoding in PCM. So here in practice we use the binary code. Why? Because I already shown that ones and zeros like that, the output of that encoder. So in digital, preferably you can call it as binary code. So that's why you can call it as digital ones zeros like that. Okay. So here, what are the main reasons for choosing or preferring this binary code over other codes? Well, because you're having a one number of codes up there in digital, but we choose only binary code. The first advantage is the maximum advantage over the effects of noise in a transmission medium is obtained by using a binary code, because a binary symbol withstands a relatively high level of noise. So whenever the noise is going to add, but this binary symbol withstands relatively high. Why? Here it is like this. It may be 1, 0. So whenever the noise, it means just like here the noise is going to add this. So the removing of this noise is easily when compared with other digital codes. Okay, so that's why binary symbol withstands a relatively high level of noise. And second one, the binary code is easy to generate and regenerate. So there is a main other advantages. One is it withstands the high level of noise, and another one is easy to generate and regenerate. Now we are entering into the regeneration along the transmission path. So it is nothing but regenerative repeater. So the most important feature of PCM system lies in the ability to control the effects of distortion and noise produced by transmitting a PCM signal over a channel. Why? Because after transmission, the signal enters into the channel. So where the noise will going to adds up with the signal. So whenever this noise is going to add with the signal is going to distort it. So we are going to control the effects of distortion by using this regenerative repeater. So this capability is accomplished by reconstructing the PCM signal by means of a chain of regenerative repeaters located at sufficiently close along the transmission route. So along the transmission route, for example, here I am sending the signal from this transmitter to receiver. The total distance is 200 kilometers. I am placing for every 50 kilometers, I am going to place one regenerative repeater. So totally I required 4 repeater. The 4th repeater is in the receiver. Why? Because in the receiver, the first block is regeneration circuit. So this is a regenerative repeater, and this is, so 50 kilometers, 50, 50. Okay. So this is the important feature of the PCM system, is the regenerative repeater. So here 3 basic functions are performed by the regenerative repeater. One is equalization, timing, and decision making. So the equalizer shapes the received pulses so as to compensate for the effects of amplitude and phase distortions produced by the transmission characteristics of the channel. So we already discussed whenever signal enters, noise will add. So by adding the noise, the signal is going to distort it. It will be losses their shape. So, and the effects may be seen in that amplitude and phase. So these distortions is going to compensate or controlled by the equalizer. So this is a block diagram of a regenerative repeater. So having amplifier and equalizer. So the input to this amplifier and equalizer is a distorted PCM wave. So the distorted PCM means this PCM wave enters into the channel, noise will add. So whenever the noise adds, it is going to distort it. So the distorted means it having some variations in amplitude or in phase. So these distortions we are going to compensate by using this amplifier and equalizer. So the amplifier, which is going to boost the strength of the amplitude, and equalizers shapes the pulse, and then it is going to apply to the decision-making device and timing circuitry. So here a periodic of triad pulses is used for difference of this coming pulses, and this decision is going to take by comparing those two signals. Why? In PCM, the signal is represented by sequence of coded pulses. So it may be like pulses. So these pulses is going to compare with a periodic pulse triad, and the decision is taken at the device. And finally, a new clean pulse is generated to the next regenerative repeater. Why? These regenerative repeaters are forming a chain. So for every 50 kilometers, these repeaters are placed. And the second block of this regenerative repeater is the timing circuitry. So the timing circuitry provides a periodic pulse triad derived from the received pulses. So this is done for renewed sampling of the equalizer pulses at the instance of time where the signal to noise ratio is maximum. So this is a duty of the timing circuitry. And after the timing circuitry, so the sample so extracted is compared to a predetermined threshold in the decision making device. Why? Because here we're having only 3 blocks in the repeater. One is amplifier and equalizer, and this is going to decision making device. And before this decision making device, you are going to give this periodic pulse triad is taken from this timing circuit. So here you can see amplifier and equalizer, timing circuit, and finally decision making device. So here this is our timing circuit. So the sample so extracted is compared to the predetermined threshold in the decision making device. So the decision making device having some predetermined threshold. So in each bit interval, decision is then made on whether the received symbol is 1 or 0. Why? Because either 1 or 0, I am using binary. I am using binary symbols. So the binary symbols contains only 1s and 0. So it may be 1 or 0 on the basis of whether the threshold is exceeded or not. If the threshold is exceeded, a clean new pulse representing symbol 1 is transmitted to the next repeater. So here a threshold level. this is a predetermined threshold level in the decision making device. Whenever this comparison is taken and it reaches this threshold level, then the decision making device makes in favor of symbol 1. So that's why a clean new pulse representing symbol 1 is transmitted to the next repeater. Otherwise, another clean new pulse representing symbol 0 is transmitted. If it threshold exceeded, 1 is generated. Not exceeded, symbol 0 is generated. So that's why binary is using. It is easy to generate and detection. So that is important blocks in this region repeater is discussed. And next one is receiver. So totally in the PCM it contains 3 important blocks. One is a transmitter, another one is a region repeater, third one is the receiver. So we are in the third block, that is a receiver block. So what are the operations in the receiver block? So here decoding and expanding. So the first operation of the receiver is to regenerate, is nothing but repeater, regenerate to repeater. Whatever we place along the transmission length. For every kilometers we are going to placing the regional repeaters. The first block in the receiver also that regenerative circuit. So here the regional repeater duty is reshaping and cleanup. So the receiver pulses go on last time. These clean pulses are then regrouped into code words and decoded into a quantized PM signal. That means mapped back, reverse mapping. So what are the operations in the transmitter? The reverse operation is done in the receiver. So the decoding process involves generating a pulse whose amplitude is the linear sum of all the pulses in the code word. So here we are going to decoding and expanding. So these are nothing but the reverse process whatever done in the transmitter. Okay. So next, the sequence of decoded pulses are samples representing an estimate of the sequence of compressor samples produced by the quantizer in the transmitter. We must use a subsystem in the receiver with the characteristic complementary to the compressor used in the transmitter. Such a system is called expander. Why? Because here we use a quantizer. So in the quantizer we are having two varieties. One is a uniform quantizer and non-uniform quantizer. So non-uniform quantizer not really exist. We have made some arrangements. That is, I used a compressor, the combination of uniform quantizer, then it works as a compression. Okay, so here I used two laws. One is mu law and A law for the compression of the signal. So at the transmitter, compression is done. So at the receiver, we are going to expand. Okay, so here I am going to expand. So whenever these two systems in a same block, that is a compressor plus expander, we can call it as compander. So this is a compander. So ideally the compression and expansion laws are exactly inverse, so that except for the effect of quantization, the expander output is equal to the compressor input if these two devices were connected directly, or the combination of the compressor and expander is referred to as compander. So here the compressor is used at transmitter and expander at receiver. So the combination of these compressor and expander we may call as compander. Okay. And finally, the reconstruction. So the final operation of the receiver is to recover the message signal. Why? Because my main aim is message signal. Whatever the transmitter is sending, that message signal is going to reconstruct and which is going to given to the user. So this is the main motto of this communication. So this operation is achieved by passing the expander output through a low pass reconstruction filter whose cutoff frequency is equal to the message bandwidth. Why? Here I am taking the cutoff frequency equal to the message bandwidth. My aim is to allow the message only, not the noise. Why? Generally, message is a low frequency signal, whereas the noise is a high frequency. So I am using here low pass means it allows the low frequency signals. That means the message is going to enter into the filter. So recovering of the message signal is intended to signify estimation rather than exact reconstruction. So that's why here in the digital communication system, we use estimation board more frequently. Okay. So I hope that you understand. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.